Okay, let's get rolling. First of all, word of warning. There may be some weird twists and turns today. My computer broke last night. I've never seen a Mac as broken as this thing was. I think it was a perfect storm. I run a developer beta on here because I write beta software for Apple, and it had just updated to beta 4 for the current OS. And at the same time, I had my Vision Pro and I was trying to connect to it at the same time as it was rebooting for the first time. And I don't know if the moon's aligned or whatever, but the firmware on this computer got corrupt. It would not even turn on. So I ended up having to short out the power supply in order to put it into something called DFU mode. 4 hours later, I got it, the whole OS reinstalled. So everything's a fresh install in here. So there's a chance that something I've done in the past to set something up is not currently set up. So we'll see. Yeah, it was a fun night, I guess. It's fun to geek out, but not when you like need the laptop the next morning. So I'm sitting there with my wife's little MacBook Air, using it to control this thing at the hardware level. Once you can get it into DFU mode, this is effectively just like an external board. And I had to have her machine rewrite the firmware and then get it far enough into letting this thing boot so I can then reinstall the OS. It was it was an interesting thing. Yeah.
So if you don't mind me asking, how do corruptions work like on a computer? Is it just,
Well, so I mean, corruptions, you have all sorts of different ways things are stored on a computer. So you have your solid state drives, you have your RAM, you have your firmware. RAM is when you have issues with corrupt data inside of RAM, that just you restart your computer and you're fine unless you have dead circuits in your RAM. But when it comes to hard drives and firmware, especially firmware, because firmware is much less accessible, these are effectively firmware is like uh, perpetual storage on the actual processor. A lot of times what happens is when you do a operating system update, it updates that firmware. And if something occurs in the middle of writing that firmware, power outage, a little power fluctuations, a zig instead of a zag, whatever it is, whatever gets written there isn't what it was supposed to be written there or didn't finish writing or whatever. And since your computer is entirely reliant on that firmware when you first hit the power button, the firmware effectively in older computers they used to be called BIOSes. Now they follow something called EFI, but they effectively do the handoff from your physical hardware to your operating system that's sitting on your hard drive for it to load into RAM. So if that guy is dead and you don't have the person who just does the handoff from the power button to boot my operating system, uh, you're in for a long night. Usually, I would say, it was kind of impressive at the end. I think usually what happened last night would have resulted in probably having to replace the logic board on the machine. Because they don't open these up anymore to do a direct chip replacement or anything. So I couldn't have convinced it externally to rewrite the firmware. It would have been bad news bears. All right. So remember, we will not meet for class on Friday. But you do have your midterm exam on Friday. It'll be up starting at 8 a.m. on Friday. You need to turn it in by 5 p.m. on Friday. I don't care when you do it. I know for a fact you're available during this time period. So you definitely have time to do it. But if you want to do that, schedule it differently, that's up to you. Grades will be up quickly. I expect probably by that night. Um, yeah. So in any case, just a reminder, same policy. If you do better on the final exam than you did in the midterm, I'll replace your midterm exam score with whatever you earn on the final. So this is really more of a check-in to see what you're retaining, things like that. So if you bomb this midterm, you're not out of luck you can still get an A in the class is the punchline. All right. Any questions about the exam before I keep trucking? Okay. So let's see where we left off here. I've also had to rebuild this project. Uh, I think it's currently working, but I guess we're gonna find out here pretty quick. Um, so if we remember, let me open up my scripts. Just open up Room Manager. This is the first time I think Visual Studio Code has been opened on this computer. Let's get that. All right, big enough, everybody can see it. Okay, so remember we have working with our um, singleton. So in core, we are keeping track of our player. We kind of went through this last class. Right now, we're storing our 4 exits. We want to bring that into kind of the current room the player is in. So last time we were messing with our dungeon. So here's our dungeon constructor where we build all our rooms, we add all the exits to the room, and ultimately at the end, we set the player inside of room R1. And this is kind of where we left off at the end of class. And this kind of comes back to this idea of scoping rules and something called automatic garbage collection. So let's prove something initially. Oh, perfect. Doo -doo. So what I want to do here is what screen am I looking at here? All right. What I want to do here is I want to, after we have created our dungeon, so we want to see that here inside of, was it Room Manager where the dungeon was created? Where did we make that guy? Yeah. So here in Room Manager, which is a mono behavior, which means it's hanging off a game object inside of our scene, we have our dungeon inside of the start function in there, which sort of kind of functions as a constructor. You can think of it like that, where it gets called one time right at the very beginning of that game object's life. We go ahead and create our dungeon. Notice here in the dungeon constructor, when all is said and done, all of these variables, R1, R2, R3, R4, R5, R6, these were all local variables in this constructor. So what I'm going to do here is inside of Room Manager, after we exit that dungeon, keep in mind, we know we already have the player stored in core. Let's go ahead and open up player real quick. Players know about the current room they're in. Players have a way for that current room to get set. They get set by the room object. So if I go back to room, we saw here in dungeon near the end, we told our room R1 to set the player to our player. What does the room do? The room goes in, it sets, the room remembers the player. So it has local access to the player, even though it's accessible through our singleton. But then the room also tells the player to set its room to this instance of room. So inside of player here, the player's current room will equal whatever's passed in there. So when our dungeon is first created, this effectively will be R1, room for R1. All right. So what I want to do here is I'm going to create a getter real quick for our current room. So I'm going to create a function. It's going to return a room. Let's call it get current room. And it'll, oh, look at that. Finished my getter for me. So it'll return the current room, whatever room this player is in. All right. So now what I want to do is inside of my room manager, after this dungeon is created, I want to go ahead and I want to do a console.log core.theplayer dot get current room. No, that's fine. We can actually, let's just get the current room. We'll see the pointer. All right, I'm pretty sure this is how you write to the console in Unity, but we'll find out here pretty quick. So let me go into Unity now. We'll go ahead and run our game. Notice we have this thing called console here. So sometimes if you want to kind of output something to the console just to see is something the value you think it should be at that point in time, you can do that. Let's see, can I make the text of this guy any bigger? No, whatever. So let me go ahead and run this. Oh, it doesn't like that. Is it just print? We'll Google it if this one doesn't work. Okay, well, we got the name, so it did work, but it didn't give us the funky looking memory addressy thing that we see in Java. So let's just get the room's name then. So the name for our room, it's private. Do we have a get name? We do not. So let me go ahead and give myself a get name for room. All right, so now we can ask a room to give us its name. So we'll go back into room manager and we'll go ahead and print out whatever the player's current room is his name. Let's see what we get out of that guy. We expect R1. So there's our R1. It's tiny, so I don't know if you could see it or not, but we got R1. Now, this is actually kind of important what's happening behind the scenes here. This goes back to the idea of scoping rules. And it also goes back to pointers. Remember those guys? We loved pointers, right? So we have something called automatic garbage collection. Most modern programming languages have this. This is an automated process by which the computer goes and reclaims memory that is no longer being used. Old school, like in C++, when you created new memory, either using the new keyword in the latter days or using malloc long before that, whenever you were the one who allocated memory, you were also the one who was in charge of deallocating the memory, giving it back, deleting the memory, letting the operating system know you're done with it. Okay. Now, it was extra work, but it gave the programmer a lot more control over when this actually happens. It also allowed you to maybe do some stuff that, let's assume you had a good reason for it, but technically that memory didn't go away. You may have lost access to the variable that connected to that memory, but the memory was still there. But the reality is this was something that felt very human in that when you make a mess, it's your job to clean it up. But now we effectively have somebody following us around cleaning up our messes for us. That's kind of like a Roomba, I guess. So this thing is just going through memory, looking for places that aren't currently being used. So the question is if you were the automatic garbage collector and you're walking through memory, how are you able to detect whether this particular bucket of memory is currently being used by anybody? How do you figure that out? So we're going back to the days that whoever wrote the original garbage collector, what did they have to do? Any ideas? we have something called pointer count. This is an integer that represents the number of, let's call it variables, that currently point at this memory address or at this place in memory. So we could say that if nothing is pointing at this place in memory, it's probably safe to reclaim it. But if something is pointing at that place in memory, then we can go ahead and get rid of it. So let's go back into our code here and go back into Dungeon. Inside Dungeon, this creates a memory address, right? This creates a memory. Anytime we see the new keyword, a memory address is being created. So we have a variable R1 that points to whatever place in memory this is. A variable called R4 that points to whatever place in memory this is. All right, all that happens. Similarly, we're building exits inside of our rooms. So if we go and look at, I don't think I clicked on exit yet. Let me open up exit here. When we create an exit, we pass it a, well, actually we're creating an exit to room called add exit, which takes in a direction and a destination. This guy then creates a brand new exit, variable E. It's a local variable inside of here. So E points to this particular exit. So the pointer count is 1. Then we add that exit to our array of available exits. So now not only can we get to that exit by my variable E, I can also get to it by going to my available exits at bucket, whatever cur number of exits is right this second. So now I have 2 things pointing to that exit in memory. The exit exists once. It's up there. It was built 1 time. So it's floating up there in memory. I can get to it through E, which is going to die at the end of this function. Right? Add exit ends here in a second when we get to the closing curly brace here. Or I can get to it through this array, which remains alive as long as this instance of room remains alive, right? Because that's a local variable. That's a field of my room object. So now I then increment my current number of exits, whatever. So add exit then ends. So add exit created a brand new exit and then preserved the pointer to that exit by having our array connect to it. So we have, for this exit, we have a pointer count of 1, a pointer count of 2. Then at the end of this function, this local variable E disappears. So now we're back to a pointer count of 1. And since it currently has a pointer count of 1 pointing to that place in memory, wherever it is, where that exit lives, automatic garbage collection will not get rid of it. Something still points to it. Okay? Only if it goes down to 0 and there's not a programmatic way to get to that place in memory does garbage collection say, I'm going to go ahead and clean this up. So going back to our dungeon then, at the end of this constructor for dungeon, all of these variables disappear. R1, R2, R3, R4, R5, R6, all of them lose a pointer counter. Each one of them contains an array of exits that also will disappear because it will go away with the rooms, right? So now that array of exits no longer points to those exits. So their pointer counts go down as well. Those are all created right here. So without this line right here, all of those rooms and all of those exits were built and then immediately collected or shortly collected. Our memory Roomba goes around it's a very low priority process, so it doesn't slow down your computer. It just kind of runs in the background and sweeps up memory as it can. Okay. But if I don't let the player know, well, if I don't let R1 know about the player, which didn't fix the problem, but if I don't let the player know about R1, So if I go back into room here, so R1 has a function called set player. If I go into room, which is R1 is an instance of room, and we look at set player, R1 becomes aware of that player. But if this next line is not here and the player does not point to R1, R1 will die. At the end of that dungeon constructor, R1 will go away. Because as of right now, if we do the count, this memory address currently has a pointer counter of 1. R1 points to it. Still a pointer counter of 1. R1.setPlayer, we go into our room. R1 now remembers the player, but R1 still has a pointer count of 1, the memory address associated with it. But then right here, when we tell the player about R1, when we tell the player to set their current room to whatever room we passed in, now the memory associated with R1 now has a pointer counter of 2. The player knows about R1 and our dungeon constructor knows about R1. As soon as our dungeon constructor dies off, we have a pointer counter of 1. The player's knowledge of R1 is the only thing keeping R1 alive from garbage collection, cleaning it up. Well, what about the rest of our rooms? Why are the rest of the rooms then gone? Well, R1 has an exit to the north that knows about R2. So we kept a program counter for that one, right? R2 has an exit to the north that knows about R3. So we kept the program counter alive for that one. R3 has an exit to the west, to the north, to the east, to the other rooms. So by way of room R1, R1 was the gateway drug to the rest of our rooms that kept one extra pointer count alive so that those local variables didn't lose, that they weren't the last way of getting to those places of memory. Does that make some sense? Important concept, but a little bit of a cryptic concept, right? Because in order to kind of understand what's going on there, you had to understand what program counting means, how automatic garbage collection works. Because if we have a place up here in memory, but we don't have any variables that let us get to that place, with a modern programming language, we can't rely on that place staying alive. Since automatic garbage collection is a low priority process, it is possible for a period of time that that memory is still reserved, but we have no direct way of getting to that memory. If you want to take more of a, modernly they're called like white hat hacker type mentality, where you're looking at ways of circumventing processes in the system or something. You could create a pointer that's early on in memory and just start hopping through memory, checking to see if there's data there. Most of the places in memory are going to have probably initialized to 0 is the data that's there. But if you go back to older operating systems, you sometimes could find parts of a file, things like that, because we weren't as good at initializing or zeroing things out, that kind of stuff. But regardless, you're kind of like going through, looking for a needle in a haystack, because you don't have any direct variables to get there. You're just kind of wandering around and checking, which is how a lot of I probably mentioned this before. A lot of like bots and things like that for video games, when people try to automate video games, cheat at them, a lot of them rely on knowledge of memory addresses, hard-coded memory addresses in the operating system that adds performance to the video game, but also opens it itself up to it being found, it being discovered. It adds performance by having a hard-coded memory address. You no longer have to dereference the pointer. You don't have to go and say, here's a variable, holds a memory address, I'm going to dereference it to get to the value. Now you just have the value directly. So it makes your games faster. In modern video games, it's important that we don't have any extra overhead that we could avoid, because we want all the nice explosions and stuff like that in the screen and keep our frame rate up and all that stuff. But that's how those things usually work. They're able to figure out, they'll write some program that just walks through memory and figures out where the memory address is for this video game. For different things where it's holding different pieces of information so that it can go and manipulate those places in memory. It gives itself a pointer to that place in memory. It's also the way the video game makers know that this is the case. So if you are someone who has ever used a bot or something like that for a game, one thing you've probably noticed is when a game updates, your bot breaks. You have to wait till they release a new version of your bot. Well, what are they doing to release the new version of your bot? They have a program that takes the new version of the game, starts it up, walks through memory, and figures out where they move the memory addresses to. They're just trying to move stuff around to keep it be a moving target. So once you think through all that, it becomes much more simplified, right? It's a hide and go seek game is how these bots work. All right. So in any case, that's how automatic garbage collection works. All of our modern languages are going to have that. So if we have a thing in memory that we need to access later, we need to make sure that we have at least one thing pointing at that place. So you want to be able to ask yourself, when we finish this constructor for dungeon, do I have a way, if I don't want these rooms to all disappear, do I have a way of getting back to these rooms? The way we have it set up right now, we're kind of indirectly getting back at those rooms, right? Now, if that wasn't as obvious to us, so maybe a less experienced programmer or something like that might have said, well, I it's a little bit confusing how all these things, like player knows about R1, R1 knows about R2, R2 knows about R3, all those things. You could just say, okay, I'm going to throw an array up here in dungeon and just store all my rooms in that. So as long as my instance of dungeon is alive, all my rooms are alive, because I know I have at least one pointer to every one of those rooms. Even though now we know there's at least 2 pointers for every one of those rooms if we did that type of approach. There's nothing wrong with it. You're being a little wasteful with memory, but memory addresses are not that big, right? This room exists exactly one time in memory. We just have multiple ways of getting to it. Multiple roads lead to that guy. All right. So it's not like we're building 50 rooms. We're building one room and giving ourselves 50 different ways of getting to that room. Or in this case, potentially 2 different ways of getting to that room. All right. So questions about automatic garbage collection and pointer count. Go ahead. 100%. It is dynamic memory. Yep. The new keyword creates dynamic memory. Pointer count allows us to keep track of dynamic memory collection, getting it back. If we didn't have that, we'd have to restart our computer anywhere from probably every couple of days to every couple of months, depending on how you use your computer and how much RAM you have. Because eventually you will have requested all your computer's memory and you will no longer have any more memory. If it's never reclaimed, if you over a month's period, you run 500 different programs or even the same program multiple times, every single time you do something, it's going to ask the operating system for more memory. And if you're never getting that memory back, eventually you're going to run out of memory. Then you just restart your computer. What does that do? It dumps everything that was in RAM, and now you start over. You got a fresh bucket of memory. Everything's been reclaimed because you restarted your machine. And I think I even told you stories from if you were a C or C++ programmer in 80s, 90s, well, especially the 80s. It was still a problem in the mid 90s probably. But you might be working on your homework and literally crash your computer because you didn't have protected memory inside of your computers. You didn't have applications running inside of their own little virtual machines to protect them from the bad things happening elsewhere in your operating system, where if they were going to crash, they gracefully crashed in and of themselves, right? Back then, it was you might have imagine as a beginning programmer, you make a lot of syntax errors, right? And sometimes you don't make syntax errors, you make logic errors. So imagine you writing a loop that just keeps generating memory. We just keep creating room after room after room after room, adding it to the end of an array or something, so we don't lose the program, the pointer count. You are literally claiming all of the RAM on your computer. While true, create room, create room, create room, create room, create room, create room. Eventually, you run out of memory. Well, is that going to crash your computer today? It won't. And this is actually, I think, information to keep in mind, because as you get out into industry, you start writing larger applications, you may have to adjust the amount of memory provided to your application by various runtimes. So for instance, when we were writing Java programs, our program runs inside of something called the Java virtual machine. When you're doing C#, it runs in something called the .NET component architecture. It's the Java virtual machine, same thing. All right. And what it does is when that Java virtual machine spins up to run your application, it has an amount of memory it allocates for your application. And your application cannot go beyond that amount of memory. It's not bound by your system RAM. It's bound by the default memory that the Java virtual machine runs your applications in. And if you need more than that, you have to then give command line arguments to the Java virtual machine to say, okay, the 256K of RAM you gave me for this is not going to cut it. I need 40 megabytes of RAM, or I need 20 gigabytes of RAM, whatever it might be. So you can pull this off, but understand that under the hood, there's a lot of things running on your computers that attempt to protect you from yourself. And sometimes those things also become limiting factors when you are trying to do something bigger. And so put this away somewhere in your brain, that if at some point in your career you are trying to do something bigger and your Java or C# program just keeps crashing, you're like, there's nothing wrong with this. Very likely is because you ran out of the allocated memory that the virtual machine gave you, not that you're out of RAM on your computer. This is especially true if you do a lot of things recursively, because recursion adds you're using a lot more memory. So fun things. Those are also the hardest bugs to find. So that's your hint to throw it into the back of your mind, because you might sit there for a long time staring at the code, wondering there's nothing wrong with my logic. There's 9 lines of code here. There's nothing wrong with that. Until you finally stumble upon the actual issue when you go and you look at the system panel and Unix, you just type in top and it shows you the programs that are currently using CPU and RAM, and you'll just see something sitting at the top showing your memory things like, that guy's only using 400 kilobytes of memory. Well, that's because that's all the virtual machine gave it. If you need more than that, you need to tell the virtual machine you need more than that, and then it'll give you more than that. Java also has the ability to run your application in what's called a server mode, which I think by default gives you elastic memory, which it'll grow as needed as you request it, but it kind of keeps an eye on what you're doing, so it doesn't, that whole infinite loop of generating RAM doesn't get out of hand if you're running into that. So it's a fun thing, but a lot of times the biggest headaches deal with things that are there to protect you from yourself. Okay, so pointer count, important for us to understand, even though it's something that happens automatically behind the scenes for us. But we do want to keep things in the context of, I have a variable, I might need that data again later. Do I have a way of getting to it? If I don't, it's going to be cleaned up. So we need to make sure we have a way of getting at that data. Okay, so we're all good with the fact that because of this one line here at the end of our constructor, we have maintained a chain of knowledge going from our player to room 1 to room 2 to room 3 to 4, 5, and 6. All of them have at least one thing that points to them, so they stay alive. We're good with that? Okay. So that means we don't have to worry about creating an external array here holding all of our rooms. The cop-out version of this might have been we could have just thrown up in core a array of rooms and just said, like, look, core is going to stay alive, so we're just going to throw everything we don't want to lose up there. That gets back to the advice I said we're it's easy to abuse singletons. So try to be a good steward of your computer's memory, or at least know that you're not being a good steward and just say you don't care because you just need to get the program done or something like that. Okay. So what we want to do is instead of our rooms having the exits turned on or turned off based on these hard-coded variables that we have here in our um, uh, in core, we instead want to have the rooms turned on and off based on the player's current room. So we need to be able to ask a room what exits should be lit, should be on, what exits shouldn't. Okay. So we need a room to be able to deliver that information to us. Now we can do it. I'm going to kind of do this in a, how do I want to do it? I'm going to do it in a fairly verbose way. So we're kind of taking a little mini step from what we're doing right now. Inside of core right now, we have 4 different variables, each representing one of our 4 possible doors. I'm going to, just for the sake of making the tiny transition, inside of room, I'm going to create 4 different functions. Um, uh, well, actually, I can create one function, but you pass it the direction asking, is there a door to the north? Is there a door to the south, west, east? And then that function will go and check that room's array of exits and find out. All right, so let's focus in on room here for a second. So in room, we're going to have a function. We'll make it public. Bool, Boolean in C# is just the word bool. C++, it's bool, all caps. Java, it's Boolean, blah. And we're going to say has exit. And we're going to pass in a direction. This should return true if there is an exit in this room leading to that direction. It should return false otherwise. So what do we want to do? This room is going to go through all of its exits to find out if that's a true story or not. I don't think we're using the doors array yet, are we? Yeah, let's just pretend like that guy doesn't exist for the moment. Focus on this. All right, so I have this array here called available exits that can have up to 4 things in it, but we know that there's only cur number of exits number of things in there based on how many exits we've added to that room, because we're using plain Jane arrays and not a elastic thing like a linked list or an array list like we looked at in Java. C# has all that crap, but as intermediate programmers, we want to have to deal with the puzzle that's put in front of us, right? So this is good practice for us. So inside of here, we want to write our loop. So for int I is equal to 0, I is less than this dot. I copied it. Cur number of exits, I plus plus. Man, this thing really wants to do a lot of crap for us, doesn't it? Look at that. No, I think is that Copilot? I mean, that's our function. Yeah, so I mean, what this function is going to do is it's going to go through every bucket of that array and say, is the exit that's in that array's direction leading in the same direction as we passed in here? And it even has our bailout, the return false. Yeah. I actually, well, you might be right, but I'm pretty sure this is Copilot. I mean, this is full-fledged code writing. That's ridiculous. Yeah. I would be careful about using this. Once you've been coding for a while and you can appreciate what this is doing for you, that's great. Although I'm not overly skilled with the whole tab to complete thing. I don't like that. But So I can appreciate how much of this just wrote all of it. But you want to practice this logic yourself, right? You want to be able to write through this. Okay, so what are we doing here? We have our stock for loop, start at 0, go through all of the exits that we actually have, which is up to current number of exits minus 1, increment I each time. Each time through, ask the question if the available exit we're currently looking at, the one at bucket I, has a direction. And actually, let's see, let's just make sure exits have a get direction and it didn't just you're not even correct. It doesn't have that. So it guessed that we had already given ourselves a getter in our exit, but we didn't. So you see here in room, it's assuming we have a dot get direction from an exit, because this dot available exits at bucket I, that guy right there, will boil down to an instance of exit. We then need to get the direction that exit heads from that exit. It's making the assumption that we must have a getter called get direction in there. Go ahead and copy that. But we look at exit, we don't have that. And our direction is private. So if we want that code to be able to access the direction our exit goes, we need to provide that getter. See, that kind of almost makes it worse, doesn't it? It shows you what the code should be, but assumes that you must have written something well someplace else. I didn't even type anything yet. It just knows what I want. All right, so there we go. We got our getter, get direction. We'll get off topic for a second. How many of you have seen the movie Bill and Ted's Excellent Adventure? A couple of you. So this reminds me of kind of a funny thing. Near the end of that movie, remember when Genghis Khan is in the sporting goods store with the bat? So this is a person from history and he's used to his older primitive weapons, right? And all of a sudden he has this like Easton's all metal baseball bat. He just starts going to town. He's just ripping stuff apart in the store. I kind of feel like that. Like, I've been programming since I was 9. And I'm a little older than that now. So I feel like what is this magic? It's just showing up in front of me. So I don't know. I guess I kind of like it, but I don't know. I feel like more times than not, it's going to fill in something that I then run into a problem someplace else. So it just creates a hide and seek type of issue. I'd maybe encourage you to figure out how to disable that in your, it's probably called Copilot. I kind of remember when I was setting this up last night that I hit yes on something, but that you're not going to learn anything having it write all that crap for you. Or you're going to spend a lot of time debugging the stuff that it thought you should have instead of what you actually had. All right, so we're going to give ourselves a getter inside of exit that will give us the direction that this thing is leading. Now that we have that back in room, we can say if the current exit we're looking at's direction, calling our public getter. Now, this is another thing. In this case, this would work. What's the double equal sign? Go ahead. Comparison of what? It's the equivalence operator, but comparison means the same thing. What are we comparing with the double equal sign? What does it work on? That's what we're trying to do here. But if we take this context out and we just say, here's this operator, the double equal sign. It is the equivalence operator for checking to see if what is equivalent to what. What kind of animal is equivalent to what kind of animal? Go ahead. Not just integers, primitive types. So anything that's a primitive type. So primitive types, that's our byte short, int long, float double, Boolean, char. Strings are weird. Remember we first talked about strings. And this is worth discussing again. I know I have talked about this before, but it might have been a while when we first started looking at Java. In this particular case, this will work. And the reason is this. Let's go draw a picture. So if I say string S is equal to north, like that, what that does is it creates a place in memory and it puts an instance of string up there. So we would say that this guy points to that place in memory. Now, if I say string S2 is also equal to north, what this does not do is it does not do that. It doesn't create another string in memory and point to that. Instead, it says, oh, I'm going to go look at my literal space in memory, a kind of a reserve space for all your literal values, like all your numbers in there, 0 through 9, all your alphabet is in there. And now strings as they come into existence get put in there. So what is actually happening here is it sees that there's already a north there. So if I then had code that says, is S equivalent to S2? No. That's not even using AI. It's just frustrating. So is S equal to S2? The answer is yes. But it's not because they're both equal to north. It's that the primitive value that S holds is a memory address. The primitive value that S2 holds is a memory address. The string itself lives at that memory address. What this is doing is it's saying, is this memory address the same as this memory address? In this case, it is. But let's assume that I had a string S3, and this was equal to a new string north. Because I invoked the new keyword, I'm saying, don't do this for me. So this code right here and this code, while mostly accomplishing the same thing, accomplish it through two different mechanisms. I usually refer to this as syntactic sugar. It's giving us a nice quick shortcut to build strings because we use strings a lot, no problem. I'm not encouraging you not to use it this way, but in the back of your head, you need to know if I'm relying on Java to manage my strings, it's probably not going to create two different norths. It's going to create one of them. Whereas if I use the new keyword, it's going to give me a separate north in a separate place in memory, which means that S equal to S3 would be false. So that's false, whereas this one is true. That makes sense? So that equivalence operator, that double equal sign, is for comparing primitive types to each other. All right. So we'll stop there. No homework over break. So remember, we will not meet on Friday, but you have an exam to take on Friday. So I will see everybody on Monday after spring break. If you're traveling, travel safe, yada, yada, yada. And I will see everybody later. I'm going to go and create a bug in my code real quick so I remember where we left off. There, that'll be a good one. We'll just throw that guy in there. That's not going to work. All right. Yep.